Hello everyone, this little video tutorial will talk about, as the title suggests, solving trig equations. So let's start off with a fairly simple one, but not just a total giveaway. An equation here, 2 times the sine of x minus 1 equals 0. Well, at first glance, and you're trying to solve this equation, you might recall some of your basic algebra maneuvers, and what you might try to do always when you're solving an equation is to isolate the variable. Well, there's our variable there, x. So let's just see what we can do. We can add 1 to both sides. All right, plus 1 plus 1. I get 2 sine x equals 1. And you're already ahead of me now, probably. Dividing by 2, and you get sine of x equals 1/2. Okay, so sine of x equals 1/2. How do we find the solutions? Well, if you recall, on the unit circle, the places where the sine equals 1/2, let's take a look at that. Here's the little unit circle. Sketch one of those. And where sine equals 1/2, well, let's see. That's right here and right there. That's at pi over 6 and at 5 pi over 6. So our solutions to this equation are x equals pi over 6 and 5 pi over 6. Lovely. And we might think that we are done. However, the fact is that we are not done. We've gotten 2 solutions off the unit circle, but as you're going to see in a moment, that does not quite cover it. There are a lot more solutions to this equation, and we have to have a succinct way of describing all the solutions. So that's what we're going to take a look at next. I'm going to use another example here, one that just kind of bypasses all the algebraic maneuvers and goes straight to isolating the variable. And what I'd like to do here is show you, not the unit circle this time, right away anyway, but show you a graph of cosine and a graph of y equals 1/2. So here we are, we've got our graphs now, and you can see the blue cosine curve, y equals cosine x, and the, I guess we'll call it yellow, the yellow straight line, the horizontal line, y equals negative 1/2. And so you can see that these two functions intersect each other in several places. There's an intersection place, there's one, here's another one, here's another one, here's 2 more, and there's another one over there, and of course, going off the screen, there are an infinite number of places where these 2 graphs intersect each other. And you recall perhaps from back in Algebra 1 that when 2 graphs intersect, that point is the solution to that system of equations. And we don't necessarily think of cosine of x equals negative 1/2 as a system of equations, but we certainly could. I can write y equals cosine x and y equals negative 1/2, 2 different equations, and the solution is where those 2 graphs intersect each other. So looking at our graph a little bit more closely, the cosine curve has the end of one cycle right there, which, as you recall, is 2 pi. Okay? And so these 2 solutions right here clearly fall within 1 revolution of the unit circle. So let's just take a look at the unit circle here, and I'll show you kind of, let's see, there we go, that's pretty good. And let's draw in a little our axes here. And so cosine equals negative 1/2 over here, right? Let's see. Cosine equals negative 1/2 right about there and right about there. And this angle here is 2 pi thirds. And this one down here is 4 pi thirds. And that's what these 2 points right here represent. The numbers 2 pi thirds and 4 pi thirds. Okay? So we could say then the solution to this is x equals 2 pi thirds and x equals 4 pi thirds. And we would have found the 2 numbers between 0 and 2 pi. But as you can see, there are all these other solutions here. So how do we account for them when we describe the solution to this equation? Well, this is how it works. If you take a look at these points, one of the things that you'll notice is that there are like separate little pairs of them, like this pair and this pair, all right? The distance between those two is 2 pi. And if I picked a different pair, let's say this one and this one, the same thing is true. The distance between them is 2 pi. And I can come up with all these other pairs. The distance between them is 2 pi. And so here's another pair right here. Distance between them is 2 pi. So it seems like from these two solutions that we got off the unit circle, if you go 2 pi in either direction from these points, you find another solution. We start off here, we go 2 pi, we find another solution here. We start with this one, we go 2 pi to the left, we'll find another one here. To the right, we'll find another one, and so on and so on. So the distance of 2 pi from each one of these beginning points right here that we have gives us another solution. So this is how mathematicians have decided to cover this. All you have to do is, from the solution that you get from the unit circle, just add the expression 2 pi k. 2 pi k. And it is assumed that k is an integer, meaning that every time you multiply 2 pi by an integer and add that to our original answer, such as 2 pi thirds, we'll find another solution to this equation. Okay? So this little expression right here, plus 2 pi k, that is the simple and very effective way of covering all the bases to find all the solutions to these equations, because literally there are an infinite number of solutions to these equations. So we start from the unit circle, and then we add this plus 2 pi k to our answer, and that pretty much covers it. So I'm going to do another couple of examples in this video, but from here on out, all that we're talking about, folks, is just doing a few different kinds of algebra techniques to arrive at this point right here, where you have isolated the variable. And once you isolate the variable, the solution comes from the unit circle in most cases, and then you add this 2 pi k thing to it. So, with that in mind, let's take a look at another example. Here's an example, and this looks like a real quantum leap in complexity, doesn't it? Instead of just saying cosine equals 1/2 or sine equals 1/2 or something, we've got something a little bit more, well, geez, it looks a lot gnarlier of a problem. But what I want to emphasize here is that this is just a matter of using a different algebraic technique to isolate the variable. And you will call upon all those techniques that you have learned over the years, students, to solve these equations. But they are familiar techniques to you. For example, in this one, we have a binomial, cosine x minus 1/2, times another binomial, 2 sine x plus root 3, equals 0. And you remember that when two binomials multiply together equals 0, that means that each one of those binomials can be considered to equal 0. So if I took this first one and just wrote that out, cosine x minus 1/2 equals 0. And did the same thing for the other one. 2 sine x plus root 3 equals 0. Now I've got a little bit simpler equations to deal with, don't we? So let's solve this one. Add 1/2 to both sides, and you get cosine x equals 1/2. Over here on the other equation, 2 sine x plus root 3. Okay, well, I'm going to subtract root 3. So 2 sine x equals negative root 3, and then divide by 2, of course. All very familiar algebraic techniques. Nothing really fancy or special here, even though when the problem started off looking pretty scary. Okay? But when we get to our solutions here, cosine x equals 1/2, and sine x equals negative root 3 over 2. Go back to the unit circle. And where are those numbers? Okay, so cosine equals 1/2. Let's call that right here and right there. Okay, so that means x equals pi over 3 and 5 pi over 3. That's where cosine x equals 1/2. And then for the other other problem. Let's see, the sine one. Sine x equals negative root 3 over 2. Gee, that's right there and right there. So there's two of them. So for this one, we kind of get a little twofer here. We get x equals 4 pi thirds and 5 pi thirds. So we had one answer that kind of overlapped. That's okay. So when we write all of these answers, the only thing that we have to do, extra special, is to add that plus 2 pi k. So our final answers might look something like this. Just x equals the set pi over 3, 4 pi thirds, and 5 pi thirds plus 2 pi k. And that will cover all the bases there. Okay? So that wasn't so bad, really. Let's take a look at another one. And in this example, we will take advantage of some of these trigonometric identities that we've been discussing in our class. So here's the equation. It's 1 plus sine x equals 2 times cosine squared x. Well, I have a little bit of a problem here. I have sine x and then I have cosine squared x. I need to have, it would be much easier for me if I had sine and sine squared or cosine and cosine squared. And so what I'm going to do here is replace cosine squared with 1 minus sine squared. Cosine squared equals 1 minus sine squared. All right? That's one of our trigonometric identities. So we will replace that. So I have 2 times 1 minus sine squared x. Okay, so that gives me 2 minus 2 sine squared x. Well, it's still looking kind of complicated here, but at least I got everything in terms of one trigonometric function, sine. So now, though, I notice that I've got sine and sine squared. Perhaps this is in sort of a quadratic form here. Let's do everything. Let's just try subtracting this whole left side of the equation. Subtract 1 plus sine x from both sides. And what I wind up with now is 0 equals 2 minus 2 sine squared x minus 1 minus sine x. That's what I get when I subtract everything from the left side and move it over to the right-hand side. When I simplify that right-hand side now, okay, I've got negative 2 sine squared x minus sine x, and then 2 minus 1, I have a plus 1. And just to make it a little bit simpler for myself, I'm going to multiply the entire equation by negative 1. That's just going to make, I'm especially looking at this right here, this negative 2. I don't really like to have a negative quadratic term in my equations. That's a personal preference, I suppose. But anyway, my equation now is going to turn into 2 sine squared x plus sine x minus 1. So let's take a look at that, this equation right here, and see what we can do with that. So 0 equals 2 sine squared plus sine x minus 1, and doggone it, that really is a rather simple quadratic form. And if you factored that expression just as if it was something like 2x squared plus x minus 1, all right, when you factor that, that one turns into 2 sine x minus 1 times sine x plus 1. So now we're back to where we were before. I can set each one of these factors equal to 0 and solve for x. So I have 2 sine x minus 1 equals 0, and sine x plus 1 equals 0. So we can quickly get to sine x here equals positive 1/2, and over here sine x equals negative 1. And so our two values that we would get for the first equation here are x equals pi over 6 and 5 pi over 6. And over here, sine x equals -1 only at, let's see, what is that? 3 pi over 2. 3 pi over 2. So our final solution then, x equals, and I use this set notation here to save myself a few pen strokes, pi over 6, 5 pi over 6, and 3 pi halves, close that set, plus 2 pi k. And we're done with that. So we'll look at one more example. That'll do it for this tutorial. It's already longer than any one that I've ever made before. But anyway, here's another example, again, using one of the identities that we've been discussing recently, namely the double angle formula for sine. You notice this equation, sine of 2x minus cosine x equals 0, has this sine of 2x. It's got the double angle expression for sine. So we can change that. Sine of 2x equals 2 sine x cosine x, and then minus cosine x equals 0. And one thing that I notice about that, they each have cosine x in them, so let's try factoring that out. So I have cosine x times 2 sine x minus 1 equals 0. Aha, we're back to the zero product property. That means that cosine x equals 0, or 2 sine x minus 1 equals 0. We've done that a couple of times already, so let's just kind of cut to that. That would be sine x equals positive 1/2. So we can see our answers here where cosine x equals 0. That is at pi over 2 and 3 pi over 2. And sine x equals 1/2 at pi over 6 and 5 pi over 6. So that is the complete set of our solutions there. X equals the set of, let's just go in order, I guess, pi over 6, what would be next? Pi over 2, then 5 pi over 6, then 3 pi over 2, close the set, and plus 2 pi k. Voila! Hope you enjoyed that. See you next time.